Good afternoon, and thank you for joining us for today's Kenworth Northeast Training Academy. We appreciate you taking the time to hop on the call with our friends from Donaldson to learn more about heavy-duty truck filtration for today's complex engines. My name is Melinda. I'm the Director of Marketing here at Kenworth Northeast. You've likely received a few emails from me leading up to today's call. And more importantly, we're joined by Gabe Blevens, from our trainer from Donaldson, who will be leading today's session, and Patrick Tellier, our Donaldson Territory Manager. So your cameras and audio are defaulted to off to reduce background noise. Gabe will be sharing a lot of great information today. So if you do have questions, I encourage you to click the Q&A icon on your Zoom browser and submit the questions there. And then throughout the call, we will keep an eye on that and answer them as we see them come through, or towards the end of the call, we'll hit them all at once. And in addition to today's session, we also have some more going through October of this year. So if you're interested in hearing from any of these other vendors that are coming up, you can log on to kenworthne.com/training-academy to register. In July, we'll be hearing from Hendrickson to learn more about advancements in vocational suspensions, including the features, changes, and proper maintenance. If you've got a Kenworth spec for vocational use, there's a high likelihood that you've got a Hendrickson suspension in it. All right, so with that, we'll go ahead and turn it over to Gabe.
All right, good afternoon, everyone, and thanks for joining us. So today I'm going to talk about something that I call shifting maintenance mindset. And what I want to do is give you some takeaways, some different ways to think about filtration, and by doing so, show you some ways that you can actually save money in the long run. So let's begin with this. And here's our agenda for today. We're gonna kick it off with that shifting maintenance mindset. And really that's about thinking about filtration in a different way. And if we do that, we're also making more informed buying decisions, which I'm a big fan of. We'll switch into something called language of filtration. And that's really translating the technical part of filtration into, what I call usable info or usable language. And then we'll wrap up with some service and best practices. And that's some often overlooked ways to save money. So let's get into shifting maintenance mindset. What is that? Well, typically we think about our maintenance process as what are we doing and when. So it's, if we don't think about it any deeper, it's just what are we doing? Let's get it on the calendar. And what I like to do is think about it a bit deeper than that. And that is, why are we doing it? And what are the parts used in that process? And if we do think about it deeper, we're going to think different about the filtration portion of that. So that's the parts used in that. And again, it goes back to why are we doing it? So let's get into that in a little more detail. And I'm going to start with this. When we purchase parts, we're influenced by a few factors. I'm going to go over some kind of high-level things that we're influenced by when we go to buy parts for our vehicles, and especially filtration. I'm going to start with price. Price tends to be number one. If we're not thinking real deep about our maintenance process, we're not thinking about why we're doing it, well, price is going to be our biggest influencer when we buy filtration. And that's because we're not really thinking about what filtration is doing for us. And there's a lot of myths out there, and I want to break some of that down today over the next hour that we have together about filtration. And some of those myths are that, well, filters are pretty much all the same, so I just want to buy the cheapest one. So I want to get us out of price as being our biggest influencer. Let's talk about some other things. How about habit? Habit's a big one. We tend to get into habits of buying, and sometimes that's, when it comes to filtration, sometimes that's based on things like name brand. For example, I may always buy the same name brand filters, and I may not really want to change that habit. And there may be some advantages to doing so, because maybe those filters that we've been buying don't offer us the best protection. So I want to give you some different ways to look at filtration today and maybe change some of those habits. Availability. Well, this one's a huge one, as we all know, over the past couple of years with all the supply chain issues. So sometimes we're forced to buy things that we wouldn't normally buy just because of lack of availability. Well, this is starting to change, though. Inventories are starting to come back up, and availability, although it's been a big factor the last couple of years, that's starting to change. So now the good news is that gives us a few more options. So availability, if it's been one of our influencers, maybe even a habit over the past couple of years, we have an opportunity to change that starting here very soon as inventories come up. Last, knowledge. So knowledge is one that, I'm a big proponent of becoming a more informed buyer in everything that I do. I like to research stuff. Unfortunately, we find that when it comes to filtration, it's often a lack of knowledge that people are influenced by when they're purchasing filters. And that lack of knowledge, really what I mean by that is they don't understand the technology behind the filters and what filters are doing for them. So it's that lack of knowledge that I believe, and this is what I'm on a mission to do, is change. I want to help folks like yourselves understand filtration better. I want to raise your knowledge level so you can make more informed buying decisions. Now, let's talk a minute about diesel engines and how they've changed. And diesel engines have changed because of emissions regulations, set by the government. Engines run much cleaner these days. So I want to highlight some of the changes from older engines, and that's pre-2007, to modern high-pressure common rail engines. The fuel systems have been overhauled to burn more efficiently, to make power better, to run cleaner. Injectors now are running up to 40,000 PSI on these high-pressure common rail systems. So if you're running any of these newer engines, that's what you're seeing on that injector rail is up to 40,000 PSI pressure. And what that means to you is that these new injectors, they're very susceptible to fine contaminant. And we'll get more into that in a few minutes. Exhaust after treatment systems have been added. So these are put on, of course, to make all of the emissions coming out of the back end much better, much cleaner. But they're big, complex systems. They've also raised the price quite a bit of newer engines. The fuel itself has changed. So the industry's gone to ultra low sulfur diesel. And then in some regions, the addition of biodiesel is actually mandated. And the reason I like to bring up the biodiesel portion is that typically the higher the bio content that's in your fuel, the more challenges you face running it in your engines. So as you see higher grades of biodiesel, you can expect a few more challenges along with that. And lastly, more onboard computers. Of course, we need those to run all these new complex systems on these new engines. So the reason I highlight this is that I want to make you, understand that we are very aware of these changes. We're very aware of the challenges that you face if you're running these newer engines. And although those engines run clean, they do present these challenges. So this increases the cost of purchase for newer engines. And it's something you need to be mindful of when you're taking care of these newer engines. So good filtration to protect those engines is even more critical than it used to be. Now, I want to talk about the fuel challenge a little bit more here for a moment. And these modern injectors, they're challenged by very tiny particles now. In fact, it's contaminant as small as bacteria in size. That's down to 2 micron in size. the contaminant that wears out these modern high pressure common rail injectors, it's between bacteria and red blood cell in size. So I used to be a mechanic working on off-road diesel engines. And back in the older engines, when I was wrenching on them, we used to be able to sample fuel out of a tank, put it in a mason jar, we'd hold it up to the light, and we'd look for just big black chunks in it. Well, those days are gone because you now need a high power microscope to see the size of contaminants wearing out these injectors. So it's a big challenge. And how big of a challenge is it? Well, I've got some numbers for you. Heavy Duty Trucking Magazine actually crunched the numbers on this, and it's pretty fascinating. And I want to share that with you folks today. So this chart here you're looking at are the results of what they found for replacement costs of these components you see here on the screen across all of North America for the on-road truck market year by year. And what they found was that the replacement costs for fuel injectors and the new high pressure fuel pumps on engine now, the dollar amount in replacement ends up being $2.75 billion that we spend annually. And again, that's for the on-road truck market across all of North America for 1 year. Those are pretty big numbers. And it doesn't have to be this way. We can actually do a better job and reduce that overall cost by protecting those injectors better with better filtration. Give them cleaner fuel. That'll make them last longer. So these are a few of the challenges you face in running these newer engines. And the costs can be quite expensive, especially if we have downtime to run these newer engines. So what can we do about that? Well, you can lower your TCO, that's total cost of ownership, by making more informed buying decisions. And what I mean by that is in more informed buying decisions around filtration specifically. And that's what I'm here to talk about today. So it's how we protect that engine. And I want to give you guys some good takeaways on that. So we got a poll question. Melinda, if you don't mind putting up our first poll question for the group. And I want to ask you guys something. And that question is, why do we put a filter on an engine? And hopefully everybody can see that poll now. Take just a moment and answer this question. Why do you think we put a filter on an engine? And this is not specific to fuel. I want you to think about any filter you put on an engine. All right, good. We got some answers coming in. And it looks like everybody's answered. So let's review this real quick. So we've got to protect the engine from contaminants. Yes, of course, that is the number one reason why we're putting a filter on an engine, right? All of the above. Yeah, that's actually correct. It's to reduce unplanned downtime, to reduce total cost of ownership. It's all of the above, right? These are the reasons why. So all of these are correct. So if you think about that, we're putting a filter on an engine to protect that engine, reduce our overall cost. Well, that's a really important job, isn't it? If I think about the job the filter's doing, so here's a concept for you to think about. You're actually hiring that filter to protect that engine. So we don't just put the filter on and put the engine into service and get it back out there. Think about it a different way. If it's a really important job to be done, well, then I'm hiring a filter to do that job, kind of like a bodyguard to protect that engine. So if I'm actually hiring a filter, if we think in those terms, to do a job, then I want the best candidate. So this is you got to understand, I'm a true filter nerd, right? I work for Donaldson company. I got a strong technical background. I'm a true filter nerd. So when I think of a filter, I think of it this way. I think of it as doing a job for me. And how do I know what job it's doing? I look at the spec sheets, the published performance specs for that filter. Because to me, being a true filter nerd, that spec sheet, it reads like a job resume. So if you look at this spec sheet here on the screen, notice I put resume at the top of it. Well, here's its job performance. And what it's telling me, if I look at this, in this case, we're looking at a lube filter. So this is my engine oil filter. And if I look at down here in the specs where it says attributes, and I'll highlight that with my little pointer here. And if you notice, it says efficiency, 97.6% at 15 micron. So that's telling me that at particles that are 15 micron in size, this filter works at stopping them 97.6% of the time. Well, that's a pretty good job performance. And that's a job performance down at 15 micron. So that's one piece of information. Now, I want to give you guys another takeaway, and that is, what size particles do I care about in that circuit? Because if I look at this filter and it tells me its efficiency at 15 micron, well, what does it really mean to me in my engine? And here's what it means to you. I'm going to show you the results of a study that was done. And this study measured the wear of these components you see here on the screen. So piston pins, compression rings, lower main bearings, and upper rod bearings. And what this study did was measured how much these components wear at different levels of filtration. And this chart's a little bit of an eyesore. I'm going to walk through it with you. Basically, the taller the bar on here, the more wear of these parts. The shorter the bar was the less wear of these parts. So that's good. We want to be down on the shorter bars. So here's what the study found. At 40 micron filtration, and what I mean by that is 40 micron, 98% efficiency. So that's high efficiency at 40 micron size. The light blue bar shows us that there was a lot of wear of these components. When we went to a higher efficiency filter, and what that looks like is a 30 micron filter at that same 98% efficiency, there was a 50% reduction on average of the wear of these components. So that's pretty good just by putting on a 30 micron filter versus a 40 micron filter. Well, the study also found that at an even higher efficiency filter of 15 micron, so you see how that works, it reaches its high efficiency at a much smaller size down at 15 micron. There was a 70% reduction on average in the wear of those components. So what I want you to take away from this is that if I'm buying a filter that's a 40 micron high efficiency or a 30 micron high efficiency or a 15 micron high efficiency, there's a big difference that I should expect on the life of that engine and how much those components wear. So 15 micron, to go back to that, filter job resume that I showed you a minute ago, the spec sheet, it was highly efficient at 15 micron. That shows it's a good filter for that circuit. Now I want to give you another takeaway here, and that is that sometimes the filter media, and that's really where the work's being done inside that filter, is what the filter media is made out of. But sometimes the filter media, just in how it's constructed, what it's made of, makes a big difference in performance in other ways. So I'm going to show you another study here. And this study was measuring the amount of time that oil filter is in bypass on a cold start. So let's start with what bypass is for just a moment. On a cold start of your engine, what happens is the oil is, when it's cold, it has a higher viscosity, it's thicker. And so it flows in bypass because you need to get, even if it's dirty oils, you need to get out there and lubricate those moving parts right away. So you're going to have some dirty oil that's lubricating those moving parts until the oil warms up, gets thinner, then it'll come out of bypass and now it'll start going through your filter and getting clean. So bypass simply means you're not going through your filter at full flow Instead, you're going around the filter and lubricating those parts. So if we're clear on what bypass means, here's the results of what we found. We measured the amount of time that a filter is in bypass with a really good synthetic grade media. And under a microscope, that's the picture you see on the left there down at the bottom, versus a cellulose grade media. And that's the picture at the top under a high power microscope. And cellulose based media, well, that's the most common filter media that's out there. It's a paper based, and the fibers are big, thick fibers in comparison to these tiny synthetic, they're actually nanofibers. And so what happens is you flow through the synthetic media a lot better than the cellulose media if you have a high efficiency filter. So that filter is going to come, or I'm sorry, the oil is going to come out of bypass a lot sooner with good synthetic grade media. In fact, it's 10 circulations of the sump oil sooner. That's what you're looking at on the table here. So with a good synthetic grade media, you spend less time in bypass and you're getting clean oil lubricating those parts a lot sooner. That's another thing that I can get if I read that spec sheet. Or again, me being the filter nerd, I call it a filter resume. Let's talk about downtime and repair costs for a minute. So, what ways do you work to reduce your total cost of ownership? Hopefully it's in thinking about filtration, because we can have a big impact on our total cost of ownership. So let's talk about repair costs for a moment. And we typically think of repair costs only as parts and labor. Let's say you've got a truck that goes down for an injector failure, and now you've got it in the shop. We're going to have to put a new injector in it. Well, parts and labor on one injector only, if it's a high pressure common rail, from a newer engine, you're looking at about $1,600, give or take a little bit, depending on where you are, but about $1,600 for one injector replacement. Well, you may want to consider doing all of them while you're in there. So you could easily get between $6,000 and $10,000 pretty quick on injectors if you have that kind of failure. So that's pretty expensive parts and labor alone. Well, as we look down this list, what about the material not moving? That's the job not getting done. That's going to cost me some money, because I'm going to have some sort of plan B. I'm going to have to get that job done still while that truck is down for repair. So hiring in another truck. If I'm fortunate enough to have a fleet, I might bring another one out of the fleet, but it's going to cost me some money for that. What about our customer relationships? If that job's not getting done, we may be damaging that customer relationship. And long-term effects, potential lost sales as a result of those damaged customer relationships, all this can add up and be very expensive. And then one thing that's not covered here, under the potential costs, is morale. And I always like to bring that up, because what about your morale? If your truck goes down, that can be devastating to your morale, to your business, your family's morale, because you're going to be under a lot of stress. So these things can add up, and all of that increases our total cost of ownership. So to wrap up this shifting maintenance mindset portion, I want to leave you with a couple thoughts. And really, it's think beyond the truck. So what do I mean by that? Well, all these categories you see here on the right side of the screen, all these categories really are your total cost of operation. And if we shift our maintenance mindset, and that's thinking about that maintenance process different, remember, it's more than just what are we doing and getting on the calendar. It's actually why are we doing it and what are the parts used. We can reduce our overall total cost of ownership, because any downtime affects all these categories. So that's being proactive versus reactive. Really, that's thinking about that maintenance process in a proactive way, instead of reactive, which is I'm going to put on the cheapest protection I can and just wait for something to break and then we'll deal with it. That's the reactive part. And I I'd like you guys to get out of that if anybody does think that way, and be proactive about protecting your equipment. And remember, when we put a filter on an engine, we're really hiring that filter to do a very important job for us. So hopefully that helps you think about filtration in a little bit different way, and how it could potentially save you money in your total cost of ownership. All right, now I'm going to shift gears for a minute and go into something called language of filtration. Language of filtration is really looking at some of these terms that you see here on the screen a little bit different. Learning filtration language will help you make more informed buying decisions. And what I mean by that is, if I understand some of these terms here a little bit more in depth, I'm going to understand filters more, and I'm going to understand how to choose a better filter. That's what this part's about. I want to teach you some of this so that you understand how to pick a better filter. Let's start with the concept of what filters are. Filters are designed to perform a job, a very specific job. And so you're wondering, well, you're probably wondering anyway, why am I looking at chickens here on my screen? Well, I want you to think about something. That chicken wire you see there, that actually acts as a filter. It's keeping my chickens, of course, where I want them to be. Doesn't let them get out, right? Well, it's doing another job of filtration. It's keeping predators out. So if we think about it, if we think about that chicken wire is actually a filter, and it's keeping these predators or chickens on one side or the other, that's like our contaminant that we don't want to flow through it, right? If it's like a filter. But think about it a little bit more in depth even. That chicken wire, it's actually engineered to do a specific level of filtration. So it keeps the big stuff in or out, but it lets smaller stuff through that I need to get through or I don't care about, such as feed. I can feed the chickens through the wire. The chickens can get sunlight and oxygen, of course, that they need to survive, right? So that chicken wire lets small stuff through, but keeps the big stuff out. So we're doing that on a microscopic level when we design a filter media. And I want to explain that a little bit more in depth to you. It looks like this. When we design a filter media, we design it to find a right balance of these things you see here on the screen. And that's efficiency. That's the job that's getting done at stopping particles of various sizes. Capacity, that's how much contaminant it holds. Think how much dirt could it hold before it plugs up. That's what capacity is. So that translates to life of the filter. And then restriction. Restriction is actually restriction to flow. So what I want you to consider here is that if I change one of these things, it affects the others. So if I make a filter that I'll call it too efficient, and what I mean by that is, let's say it stops everything going through it, well, then it's going to have a very short life because the restriction to flow is very high. So it's going to plug up quickly, right? And then if I reverse that the other way and I make a filter too open, well, it might have a longer life. That's the capacity, but it's not going to catch much stuff. So it's going to have a low efficiency and it will have a very low restriction to flow. So if we think about that in terms of a balance, when we design a filter media, what I want you to take away from this is that Donaldson is always striving to find the right balance of these things for every application that filter goes in. So we want it to perform high, we want to do that job well and last a long time. Now I've got a question for you, Melinda, if you don't mind putting up the next poll. And that question is, when you're going to choose the best protection for your engine, how do you do that? How do you choose the best protection for an engine? All right, good. We got answers coming in. Excellent, excellent. And I'm glad no one said I'm not sure. I haven't thought much about it. I'm glad no one's saying that. Yeah, so follow the manufacturer's recommendations. That's the number one answer. Look at the published performance specs. That's number two answer. Both these are great answers. So I want you to let's talk about that for just a second. If we follow those manufacturer recommendations, yeah, absolutely. The manufacturers say for what components are in whatever we're protecting, what level of filtration you need. That's a good place to start. That's a minimum level of protection. And I want you to understand you can actually protect stuff better in some cases. Sometimes you can buy filters that actually do an even better job than what the manufacturer recommends. But look at the published performance specs. That's how you actually know the level of filtration that you're getting. So in other words, the level of protection you're getting for that engine. So both those are great answers. Now let's talk about this a little bit more in depth. So how we choose the best protection. I'm going to give you some other possibilities here. Some of the common ways that some people think about it. Price. Is price a good one? Do we assume that the most expensive filter is always the best filter? Well, I'm here to tell you that's not always the case. It's not always the most expensive filter. Name brand. Now, this is one that I'm going to call a misconception. Actually, both these are prices as well. But sometimes we assume that a certain name brand is always going to be the best filter. That's actually not the case all the time. How about those performance specs in the catalog? We just discussed that one. That's actually the right answer. That's how we know the level of protection. So this next section, what I'm going to do is take a little bit of time and show you how to interpret those filter specs. And this will be the most technical thing we talk about today. And it's actually not too technical. I'm going to try and break it down simply. And it starts with this. When we're talking about liquid filters, they're rated at stopping contaminant of various sizes. And they use a micron as a measurement. So what are the micron ratings? Well, 1 micron is a millionth of a meter. And of course, we can't see a millionth of a meter. So here's some scaling to help that make sense. And these are average sizes, by the way. So average size of a grain of table salt, that's about 100 micron in size. A human hair, that's about 80 micron in size. That's the thickness of that hair. The next one's really interesting. Lower limit of visibility. Now, this is the smallest that we can see with the naked eye. And that's going to be about 40 micron in size. That's like a little tiny dust particle that you would see floating in the air. That's about the smallest we can see. Well, guess what? Almost all liquid filters are rated at micron sizes much lower than 40. So it's stuff that we can't see really without a high power microscope. And if we look down there towards the bottom, this is just a quick reminder for you of the size of contaminant that's wearing out injectors these days. It's down to bacteria size. So it's down to 2 micron in size. So let's get into the ratings now that we understand what micron means. There's 2 liquid filter ratings that are primarily used. This is what I want to go over today. One is called a beta ratio, and then one is percent efficiency. And they're really 2 different ways of telling the same story. That's going to make more sense in just a minute. But the way it works is that hydraulic filters are typically rated using a beta ratio. So you'll see a micron size and then a beta ratio associated with that. And then other liquid filters like lube and fuel, they'll use a percent efficiency. So you'll see a micron size and then a percent efficiency associated with it. So what are these 2 and what do they mean? Well, in real simple terms, if we look at this table here on the left, down the left column are various beta ratios. And then next to them is what, if you translate that to efficiency, that's what it means. And then in the right column is really what it's telling us. So let's look at the bottom one, because that's the easiest one to understand. A beta ratio of 2. Well, that means 50% efficiency. And what that's telling us is that for whatever size particle we're looking at, if 2 go into the filter and the filter stops one of them, so only one comes out to the clean side, that's a 2-to-1 ratio. That's where you get your 50% efficiency, or that's a beta ratio of 2. Pretty simple, right? So if we look at this table and notice that the higher the beta ratio, well, that translates to a higher efficiency. On the right is an example of that. If we take a look at this filter, and we're going to rate this filter at 5 micron, and that means at 5 micron size particles, how many go to the filter and how many make it pass? And that's what we're going to rate it on, is how well does it stop 5 micron size particles. And in this example, it's a 10-to-1 ratio. So for every 10 particles that go to that filter that are that 5 micron size, 1 makes it out. So that's a 10-to-1. That's a beta ratio of 10. So that's what you see here on the table. Down at the second to last column, beta ratio 10. That means it's 90% efficient at that 5 micron size. So that same filter, its beta ratio is going to change and its efficiency is going to change at different size particles. See how that works? So at bigger particles, it'll have a higher beta ratio and a higher efficiency because it's going to stop bigger particles better. At smaller size particles, so smaller than 5 micron, it'll have a lower beta ratio and a lower efficiency. So hopefully that takes the mystery out of what beta ratio is. It's actually really simple. The takeaway I want you to have is that you want a higher beta ratio because that means higher efficiency. If you have a higher beta ratio at a certain particle size, you're going to get cleaner fluid. Now, there's another term called absolute. That's used in ratings sometimes. If you look in the dictionary at absolute, well, really it means all of something. Unfortunately, when it comes to filter ratings, it's a little confusing because it doesn't mean all, it means what you see here. It's a beta of 75, or it's an efficiency of 98.7%. And the reason for that confusion is because this term, absolute, it comes from a really old industry test standard that's not used anymore. And in the old test standards, it did mean 100%. It did mean that at whatever size particle you were looking at, if it was absolute, it stopped all of them, then that was 100% efficiency. But since the old standards weren't that accurate, the industry's gone to more accurate ones. And so when you take that old data, translate it into new data, instead of 100%, it means 98.7. There's another term called nominal. And here's what nominal means. It means it's a beta of 2, or that's a 50% efficiency. So if you see these two ratings, I want you to understand what they mean. It's absolute is not telling you that it's 100% efficient at a size. It's a little bit less than that. So hopefully that helps with that confusion if you've ever seen it before and wondered. Now I'm going to play just a short little video recap here of that part, and then we're going to get into this a little bit more in depth. And this is just a little over a minute long. Turn the volume down.
To select the right liquid filter for your application, such as those used for fuel, lube, and hydraulic filtration, you need to know the size of the particles in microns to be captured, and the quantity of the particles being captured compared to those allowed to pass through. While engine liquid filtration performance is often defined as an efficiency percentage, Most hydraulic filters' performance refer to a beta ratio. For example, at a specified micron size, when 1 out of 10 particles passes the filter, it has an efficiency of 90% or a beta ratio of 10. When 1 out of 1,000 particles passes the filter, it has an efficiency of 99.9% or a beta ratio of 1,000. It's important that both the filter's micron size and beta ratio are matched to the application. Not enough efficiency leads to a greater risk of contaminant-related component wear and failure. Too much efficiency may result in increased operational pressures, removal of oil additives, and shortened filter life.
All right, and if anyone wants to refer back to that video, you can find that on Donaldson's YouTube channel. All right, let's get a little more in depth on the ratings for a minute and how it translates to choosing a filter. So I'm going to switch to gears here a little bit and talk about hydraulic. And when we protect a hydraulic circuit, and we want to find out what level of filtration we need, let's say there's a couple different ways of doing this. If I'm taking off a hydraulic filter and replacing it with another one because I've serviced that oil, I can usually cross over a part number and find different options by crossing the part number. And if I haven't had any problems in that circuit in the past before I serviced it, like the oil was too dirty, or I had, frequent pump rebuilds or some sort of issues. If I haven't had any kind of issues like that, crossing the part number might be just fine because you're going to get the same level of filtration. But if we're starting from scratch and let's say I don't know what level of filtration I need, or I needed to get a little bit cleaner oil, this is how we want to look at it. What you're looking at here on the left is a table that is actually published in the back of Donaldson's hydraulic catalog. And what this shows you are various components that might be found in your hydraulic circuit in that left column. And then in the right two columns are a series of numbers. What these numbers are fluid cleanliness numbers using a system called ISO 4406 contamination code. That's a mouthful. I'm not going to go into what those numbers mean exactly. I'm going to summarize it real short for you and just say that these numbers you see here on the screen in this table, the bigger the numbers, the dirtier the fluid. So for these components, these cleanliness numbers that you see are how clean the fluid needs to be to protect those components. Let's say you're just protecting a hydraulic cylinder, and you see that down here next to the pointer. You can have a fluid that's as dirty as an ISO 2018-15. Now, what that's telling me is that what I want you to understand is an ISO 20 in this case is a pretty dirty hydraulic oil. So you don't need real clean hydraulic oil to protect those cylinders. And then I'm going to show you an example on the other end of it, something really sensitive that needs very clean oil. That would be like a servo valve that you see here next to the pointer. And that's going to be an ISO cleanliness of down to a 16, or if I look over here and it's running a higher pressure in this column over 3000 PSI, it would be an ISO of 15. So again, I'm not going to go in depth on the ISO numbers, what they mean, but what I want you to take away is that the bigger the number, the dirtier the fluid. So a real sensitive component like a high pressure servo valve, that needs extremely clean oil to protect that. So I simply look on this table and see what I'm protecting or where that filter might be in that circuit. Let's say, for example, you're protecting a hydraulic circuit on a skid steer that you have maybe running around your yard doing work for you. Well, it's going to have a hydrostatic transmission in it. And that skid steer, for example, here is going to be running a pump like you see here. It's going to be a variable piston pump like this. So you're going to need oil that's pretty clean, more on the clean side to protect that pump in that circuit. So we've got a circuit over here on the right, just an example of one. This can look millions of different ways depending on what your circuit is. So this is just an example of what it might look like and different filters within that circuit and how they're protecting various components. So sometimes you have to take it a little more in depth and understand your circuit some and to find the level of protection that you need for that filter. Now, once I get this information, let's say that I've determined what level of cleanliness I need by looking at these ISO numbers and what my circuit, what I'm protecting. There's another table. It's a handy chart to use, and again, in the back of the hydraulic catalog, and it's actually near this one. And that table is actually going to show you what filter to pick to get to that level of fluid cleanliness. So it starts with what am I protecting? And then we can help guide you all the way to what filter to buy to protect those components. Now I want to look at some actual filter performance specs here and help you interpret those for a minute. And let's say that I am replacing a hydraulic filter and I need to look at some crosses. Well, the way Donaldson likes to advertise our performance is we use a beta ratio of 1,000, and then you just pick the micron size you want. And if we understand beta ratio, if you remember, 1,000 means that's where it reaches its high efficiency. So if we look at this one, this is a beta 11, 1,000. That means 11 micron. That's the size particle that we're looking at. It's 99% efficient at 11 micron. That's real high efficiency. So you just, if you understand beta ratio, you know that 1,000 means that's where it reaches its high efficiency. So I know which filter to select to get high efficiency. In this case, that's 11 micron. I want to show you some possible cross-reference material, what it might look like with some other part numbers. So let's say you cross over, you go to the fine folks at Kenworth Northeast, take your hydraulic part number into them, you cross over, and they show you some alternatives. Here's what comes up. Let's say you find one that says 11 micron absolute. That's how its performance specs rated. Well, we know that that doesn't mean that it's 100% efficient at 11 micron, right? We now understand that that means it's a beta ratio of 75 or it's an efficiency of 98.7. So that one's not going to be as efficient as the one you see here on the left. It's not going to get the oil as clean. What if we see one like this? It says that at 11 micron, it's beta 100. Well, beta 100 is less than beta 1000, isn't it? So we know that this one won't get the oil as clean. That's actually going to translate to 99% efficiency, so not as clean. What if we see this? What if it just says micron rating of 10? And this is common. You'll see that out there. Well, I don't have the second piece of information. If it just says micron rating of 10, I don't know how well it works at 10 micron. So you see where I need two pieces of information. And then what if I want to find an even more efficient filter than this? I need to get it even cleaner than that 11 micron beta 1000. Well, that might look like this. This is a cross for the same part number. And notice this one is beta 1000, but down at 4 micron. So see, it reaches its high efficiency at a much smaller size. So that tells me it's going to get the oil a lot cleaner. Now I want to switch to lube for a minute. And let's look at some different lube filter ratings. Here's my scenario. Let's say I want to put a lube filter on my Cummins ISX engine. Real common engine out there, a lot of these running around. So a lot of options you're going to have for filters. First part number I want to talk about is a P55 9000. This is a Donaldson part. And notice its efficiency is 97.6%, and that's at 15 micron. And you remember what size particles we care about. Remember, it is 15. Let's look at another part number, DBL 7900. Notice the efficiency in this one, 97.6%, again at 15 micron. So the performance there is the same. But the difference in this filter, if you notice in parentheses, it says extended service. This is really designed for extended oil intervals if you want to go past your OE recommended oil intervals. So it's designed to go longer. Let's look at one of the competitor filters. Actually, there's a few out there that are rated at 99% at 30 micron. Notice there's a discrepancy here. This one's 99%, but at 30 micron. So that's a little confusing, right? How do we know what level of protection that is when we compare it to that 15 micron filter? Well, remember the size I care about the most. It's 15 micron. That's what wears out all those components in that circuit. So if we take that same filter, look at this next line, and we measure its performance down at 15 micron, look at its efficiency. Its efficiency actually drops to 75.6%. So that's a big difference in that level of protection for that engine. Here's another part number, P550949. Notice its efficiency is the same as those competitor filters, 99% at 30 micron. And really where this one is recommended, that we recommend this will be used, is on the older Cummins engines, the pre-2010s. Those engines, they had a little bit of an issue with high soot production. They tended to plug filters early, so they had shorter filter lives. So we actually recommend going with that 99% at 30 micron, because you don't need that higher efficiency in the older engines as well. So you're okay going with that one. So here's some takeaways for liquid filters and how they're rated. Remember that most contaminants microscopic in size. So understanding the ratings, well, it's critical to understanding the filter performance. Be aware of how they're rated. Absolute doesn't mean 100%. It means 98.7%, or that's a beta of 75. And you want to look for a micron size and a beta ratio or a percent efficiency. So if a filter is rated at just a micron size, let's say it just says 10 micron, well, I don't know how well it works at 10 micron. It just says 10 micron. And finally, remember this for your injectors on high pressure common rail, it's bacteria-sized particles that are wearing those out now. Now I want to switch gears to air filters for a minute, and we're getting close to the end of our time, so I'm going to speed it up a little bit so that we make it through. And here's a concept for you. For every gallon of fuel that a modern diesel engine is burning, it's pulling in up to 20,000 gallons of air for that combustion process. That big air mass is a big opportunity for contaminant to be pulled in. Here's another concept to think about. It takes only 1 gram of dust per horsepower to destroy a diesel engine. 1 gram is about the weight of a paperclip. So you're always pulling in that mass volume of air, a lot of opportunity for contaminant to be pulled in, and you only get one chance to clean it. So keep that in mind. And just quickly, air filters and liquid filters are rated different. Air filters are not rated on individual micron sizes. What happens is you put an air filter on a test bench, you pull air through it, just like it would be on an engine. You inject dust into that air, and then whatever makes it past the filter that you're testing gets caught on a secondary filter media that's on the test bench, and that's weighed before and after the test. So efficiency in an air filter is strictly looking at mass, how much dust went to it versus how much dust made it past. So when you look at ratings, they might look like this in an air filter. These little dust vials you see here on the right side of the screen, those are about the size of your pinky finger, just for scaling so you understand what you're looking at. What I want you to take away from this is that a little change in efficiency rating, like you see at the bottom of these, is a big difference in the amount of dust actually that makes it pass. So a filter that's rated at 99% efficient, that sounds good, right? But for every 1,000 grams of dust that go to the filter, that means there's 10 grams of dust that make it to the clean side. Look at the really clean one. A filter that's 99.99% efficient means that for every 1,000 grams of dust that go to a filter, only 0.1 gram of dust makes it to the clean side. So big difference on the clean side in that little change of efficiency rating. We'll get into our last section here, service and best practices. And these are often overlooked ways to save money. I'm going to give you guys some popular misconceptions and break those down for you, break some myths today. If you don't schedule downtime, your equipment will do it for you. So let's think wise about our service process, what we're doing and when we're doing it, and remember why we're doing it. So oftentimes we don't know when the right time to service our engine is. What I want you to take away is that you can work with, again, the fine folks there at Kenworth Northeast to help you determine when the OE recommended service interval is for your engine. You can also look this stuff up online and find tables like this, and they're going to tell you when to service all these components. If we're looking to extend oil changes, plan wisely. And what I mean by that is if you want to go longer than the OE recommended interval, creep up on those intervals, go over them a little bit by sampling your oil and checking the health of that oil. Then the next time you service it, go a little bit longer and sample that oil. So you want to creep up on those extended oil intervals and see if that oil is healthy. Are you cleaning your air filter? This is not recommended. And real quick, because we're running out of time, the reason why it's not recommended is you actually damage your air filter in that cleaning process. And one big takeaway I want you to have is if you're cleaning your air filter and you're running an engine under warranty still, you actually void your OE warranty. So I want to get into servicing air filters real quick. And I'm going to show you two different examples of how to service an air filter and the difference it makes in protecting an engine. Truck one is going to service an air filter on a regular PM schedule. This is the most common way of doing it. Likely a lot of you listening today do it in this way. Truck number two, it's going to change out air filters much less frequently. Here's how truck number two gets by with it. They wait until they see red on their indicator. Now, these two methods, I want you to bear with me on what I'm about to say, because this is counterintuitive. Truck number two is actually protecting its engine better. And the reason why is because an air filter becomes more efficient over time. And if I run that filter all the way until the indicator turns red, I'm actually sending less dust onto the engine, because a dirty air filter is actually a good air filter. And you know who says that's okay to do? The engine manufacturer. It's not me, the filter guy. It's actually the engine manufacturer that says run it until you see red on the indicator. Now I'm going to pause for just a moment. Melinda, I'm going to ask you a quick question. How are we doing on time? Do we have about 5 more minutes?
We're at 3 o'clock. So if folks are able to stay on for another 5 minutes, you're welcome to stay on. There will be a recording available after the call as well. So if you want to go ahead and yeah.
Fantastic. Then I'll go through our last few minutes here. And if anybody needs to go, you can access this video later. Okay, now I want to break down another misconception, and that's about the indicators. And we tend to hear this a lot, this quote, I don't use indicators because they don't work. And I'm going to show you a little video clip of why that likely is. In this video, I have this air cleaner, and I'm going to pull vacuum through it, and I'm going to slowly restrict the intake with my hand. And that's just like plugging the filter up with dust. And I want you to watch the gauge on the lower right. And I want you to see how long it takes for that gauge to get to 25. That's 25 inches of water. That's the restriction point. that where this filter would be determined to be plugged up. And that's set by the engine manufacturer, by the way. So I'm going to play the video now. Now notice I'm over halfway and the needle just started to move. Look how much I've restricted the intake. I'm almost covered up and I just now have reached my restriction level. You also see a red light that came on there that tells me that the filter's plugged. It's time to change it out. Now, I want you to understand what you're seeing here. What you're seeing is that you don't build the full restriction on these gauges until that filter gets pretty dirty. It actually builds a very big layer of dust on it. So if we're doing visual inspections, that's not recommended because you can't look at a filter and determine how dirty it is. Because remember, a dirty air filter is actually a good air filter. And I know this is counterintuitive and it sounds kind of crazy because here is the filter guy telling you that, hey, maybe you can actually put less air filters on your engine. But guess what? I care about you protecting your engine more than you just buying more air filters and putting them in. If you want to do that, that's fine. But I'd actually like you to protect your engine better. I want to talk about evacuator valves for a minute. This is often misunderstood and overlooked. And if you have an air cleaner that's equipped with one of these, you want to make sure it's on there and that it can work. So the way these work, what they actually do is they help kick out excess dust and moisture from your air cleaner, and they help your filter actually last longer. So if they're cracked, torn, sun dry rotted, maybe missing, any of those conditions, you want to replace that. And it's on average about a $10 part, so it's pretty cheap. I would check it every so often, maybe every filter change. And I'm going to show you the importance of these with another short video. And in this video, we've got the same air cleaner. In this case, you see a bowl pre-cleaner on it, and I'm going to feed it these paper cutouts. So what I want you to do is watch what happens as I feed it the paper cutouts. A lot of them are going to get caught in the pre-cleaner there in the bowl, but a lot of them are going to go down to the vac valve at the bottom. See this? Now watch what happens when I force it open. It becomes a new inlet. So the way these work is when the engine is actually running, those evacuator valves, they're closed because they're under suction. So when I forced it open with my hand there, it now can't function like it's supposed to, and that's a new inlet to my housing. So if yours is damaged or it's missing, you got another inlet to your air cleaner there, and you're going to plug up your air filter faster than if that evacuator valve is on there and functioning. So I want you to have that takeaway. It's a cheap part, and it can actually save you money in the long run. And the last thing I have for you today, we'll wrap up with this, and that is how you store your filters and handle them. That actually makes a difference in protecting your engine. Just a couple takeaways for you off this. Think about if you've got boxes of filters, in your warehouse, make sure those boxes are sealed up as they were sent to you. Filters should be in a plastic bag inside of a box that's also closed. So that bag of that box should be closed up. Think about this. If that box or that bag or both are open, well, you're now a little vulnerable to the ambient conditions. You can actually build a rust layer inside that filter, maybe on the inner liner, maybe on the baffle plate, because those are made out of steel most of the time. So you can actually build a little layer of rust if moisture gets in there. And now you put it on the engine and you're going to send a rust load onto your engine. Other things can happen as well. I've been in warehouses and seen thick layers of dust on a lot of boxes, and I've seen open boxes, open bags with filters with a nice thick layer of dust. Well, guess what? That filter now gets put on the engine you're going to send that big dust load onto the engine as well. Other things to look for, like practice a good first in, first out with your inventory. So filters do have a shelf life, believe it or not. We don't want you to use filters beyond 5 years. And that's because the seal properties, that's the main thing. The seal properties start to break down over time. So we don't want that filter going into service. We'd like you to replace that filter. So make sure you're using more of a first in, first out procedure with your inventory. Get that older stuff on. Don't keep kicking it to the back of the shelf and then grab it, 5 years later. And lastly, when you open new filters out of a box, do a quick inspection. If for some reason the seal is missing off of a filter, you want to get that replaced. So we'll replace that seal for you. You don't want to use an old seal, and you want to make sure the filter's not damaged in any way. So you want to take a quick look at the filter, make sure it has no dents in it. Dents lead to cracks. Let's say it's an oil filter you're threading on. If there's a dent in that can, well, when that filter's on the engine and it's in service, it's under vibration, it's under heating and cooling cycles, and those dents, they lead to cracks, and that could be a major problem. So make sure that new filter is not damaged. All right, that's what I have for you guys today. Thank you for joining us, and hopefully it gave you some good takeaways on ways to save overall on your total cost of ownership and how to protect an engine better. Does anyone have any questions?
So I've not seen any questions come through in our Q&A, but we are over time. So I definitely thank you everybody for joining on. I'll be sending out a follow-up email either tomorrow or Thursday that'll have a link to the recording from today's session if you want to go back and reference anything. And anytime you've got a question, feel free to reach out to your Kenworth Northeast sales rep, or you can reply back to the emails that you get from us for marketing as well. All right. Thanks, everyone. I appreciate your time today.